So here is the Mathcad file for the design of a thin plate connection in accordance with NZS3404. So we've already got our forces derived from a separate analysis. And we're assuming we're going to be using M16 bolts and a 10mm thick thin plate with 6mm fillet welds all round. So as I say, our applied shear load is 40 kilonewtons. We're using a primary beam as a 310 UC 96. So here are the parameters for that. The secondary beam is a 200 PFC. Here are the dimensions for that PFC. Thin plate, as mentioned, is 10 millimeters thick, and we've got 2 bolts. I'm going to use the same grade of steel for the sections as I am for the plates, so it's going to be a grade 300. Let's go to the bolts. We've got 16mm diameter bolts, and they're going to be grade 4.6, giving us a tensile strength of 400. First, we need to check on the thin plate bolts. That's the bolts in the thin plate. So we're assuming that the bolts are in the threaded portion of the bolt. So the shear plane goes through the threads rather than the shank. So we add up the areas of the threaded portion multiplied by the number of bolts, multiply that by the tensile strength of the bolt, and it has a 0.262 factor to give you the shear strength of that bolt group. Apply a strength reduction factor and we get a design capacity of 62, which is significantly above our applied shear. Now let's look at the weld. We have a 6mm weld, which gives us a throat thickness of 4.2 millimeters. And we know what the nominal capacity of the fillet weld is per unit length, taken from the code, clause 9.7.3.10. And that gives us our 1043 kilonewtons per meter for that weld. So the nominal capacity of the fillet weld and is just the length of the weld and multiplied by the nominal capacity, and because we've got a weld each side, we double it. That gives a 367 kilonewton capacity of that weld. Let's look at the fillet weld resisting shear, and we have a utilization of 18%. Check on the thin plate resisting the shear. So the shear capacity of the thin plate itself is simply the shear area multiplied by the yield stress multiplied by a 0.6 factor. That gives us a design shear capacity of 347 kilonewtons, so quite large. Need to check the bearing. So you've got bolts bearing on the ply of the thin plate, and so the bearing capacity when given a strength reduction factor is 176. And we've got our bearing capacity simply by the diameter of the bolts with the thickness of the plates multiplied by the tensile capacity of the steel. If you've got a thin plate, it may buckle in shear, so you need to check shear buckling. So clause 5.11.5 gives you a factor for shear buckling. In this case, the factor is well over 1, so shear buckling is not going to be a problem with this particular plate. You take the minimum in any case, and then you have a design shear capacity, which is below your applied. So you can summarize that by saying your design capacity of the connection is 62.3 kilonewtons. Okay, nice and simple. You can go on to the next one.